Hello everyone, hope you're all doing well. And today I would like to prove a statement that if you stop to think about it for a bit, you see that it actually makes a lot of sense. So the statement goes as follows. If you have a circle with infinitely many points inside it, then there must be somewhere inside the circle where where there will be a bunch of points just clustered up. Actually, infinitely many points clustered up somewhere in the circle. Just think about it for a bit. If you try to place infinitely many points inside a circle, if you try to place them unevenly, there will be somewhere, like in this example, there will be somewhere where you will have to put more points, and you end up making a cluster there. And if you try to spread them evenly, since there are infinitely many points, they will actually just end up filling all of space and they will be clustered literally everywhere. So, so it's actually impossible not to create a cluster. So in order to prove this theorem, we first have to formalize a bit what we actually want to prove. Um, and what do I mean with being inside a circle and being a cluster? What is a cluster? What do I mean when I say a cluster? And let's just go through all of this quickly before actually tackling the problem. So to start off, let's remind ourselves what a circle is and how do I know if a point is inside a circle or not. So suppose we have this circle with center O. The circle is defined as the set of points with a fixed distance r from its center. So if I take any point in this circle, the distance from that point to O will always be r. That's how we define a circle. So knowing that, how can we know if a point is inside a circle or not? It's actually quite simple. Suppose I have this point P and I want to know if it's inside the circle or not. In this case it obviously is, but anyway, all we need to do is to calculate the distance between O and P. All we need to do is to calculate this distance. If this distance d is less than the radius of the circle, then P will be inside it. If d is actually greater than r, then P will be outside the circle. And if d is equal to r, then P is in the very circumference. So I'm just reminding this because this will be very, very, very useful later on. So if you want to know if a point is inside or outside a circle, just take the distance between the point and the center of the circle and see if this distance is smaller or greater than the radius of the circle. Okay? Next, I need to define what a cluster is. What do I mean with a cluster? Well, see this example. I have a bunch of points spread around here. And you could very well argue that there must be a cluster of points here. And I mean, yeah, technically you're right because there are a bunch of points together here, but that's not what I mean when I talk about a cluster. See, if I reduce the size of the circle, there will be still a bunch of points here. Okay, fair enough. But if I keep reducing the size of it, you'll see that eventually there will be less and less points. And now, for example, there are only 3 points. And if I keep reducing it, if I make it like a tinier circle, you'll see that eventually I get to a situation where basically there will be no points around it. Just 1 second. So you get to a situation where there will be no points around it. So for every point here, if I zoom it enough, there will be no points inside it. So here, there are no cluster for me. That's not what I mean when I say cluster. I'm not just saying that there are a bunch of points together. What I mean with cluster is more than that. So I'm gonna show you what a real cluster here means, at least for us. Now look at this example. Now there are infinitely many points here, and if you look at it, you see that if I draw a circle around it, I mean, there will be a bunch of points here, infinitely many actually. And if I reduce the size of the circle, it will still have infinitely many points here. And if I just keep reducing it, there will always be a bunch of points around here. There will always be infinitely many points here. If I keep reducing it, there's always infinitely many points inside it, no matter how small the circle is. So this is what I mean with a cluster. It's actually infinitely many points, so close to each other that no matter how small of a circle I draw around them, there will always be infinitely many points inside it. So with that in mind, we can actually define a cluster in a better way. We're gonna define what a cluster is here with something called a cluster point. So what is a cluster point? So look at this red point in the middle. This will be a cluster point if for every circle I draw centered at this point, there will be at least one point from this set of black points. There will be at least one point inside the circle, no matter how small I make it. I said there were infinitely many, and if you think about it, you see that there must be infinitely many points here. But I only need one, at least one. I need to prove, like, if I want this point to be a cluster point, I want to be able to draw a circle with any radius I want and have at least one point of this set of black points inside the circle. That's what I mean with a cluster point. So let's define it more formally. So a cluster point, also called a limit point or an accumulation point, is a point such that for every circle centered in that point, there will be at least one element of A inside that circle. So suppose this is the set A, and you can think of a set as just a bunch of like infinitely many points around it. But for example, this point inside of A, this point is an accumulation point because if for any circle I draw centered at that point, since it's in the bulk of A, there will be infinitely many points around it. So there will be at least one point from A inside the circle. For any circle, if I make it smaller and I center it, there will be infinitely many points from A inside it. There will be at least one point, that's what we need, but in practice there will be infinitely many. So this point is a cluster point, or a limit point, or an accumulation point. So you can clearly see that for every point I pick in the bulk of A, it will be a cluster point because I draw the circle, there will be at least one element of A, so great. If I take a point in the boundary, it will also be a cluster point because for every circle I draw, I mean, it's on the boundary, so a part of it will be outside of A, but a part of it will be inside it. So there will be points of A down here. And no matter how small I draw this circle, there will always be at least one point from A in there. So, so we have an accumulation point. One quick detail, this accumulation point doesn't need to be in the set you're analyzing. So, for example, if I exclude the boundary from the set A, so if I say that, I don't want no boundary in here, and I just delete it, the points on the boundary will still be accumulation points because they don't care if they are in or if they are in that set or not. Next, let's talk about the cluster points for the set consisting of these 4 points. In this case, there are no cluster points, and it's easy to see why. If you pick a point, for example, close to one of the points from this set, so I'm saying that these 4 points belongs to the same set. This point, for example, is not an accumulation point because I can draw a circle centered on it that has no points from the set. And I mean, you can do this like if I get a point that's even closer, I can draw like a small circle with no points in it, so it's not a cluster point at all. And if I pick a point itself, this is still not a cluster point because when we consider points close to it, we disregard the point itself. So if I take this point and I want to see if it's a cluster point, I disregard that point itself. So if I draw a circle around it, there is no point other than itself within this circle. So this is not a cluster point. We do not consider this a cluster point. If we were to consider this a cluster point, that wouldn't be so much of a useful definition, since every point of any set would be a cluster point, and that's not what we really want. We want to see if there are points that are really clustered together. So in this case, this is not a cluster point. If I take these 4 points, there are no cluster points in here. Okay. Lastly, let's talk about this set. So the set consisting of these points all lined up here. And you can see that in this particular set, the points, as you go further down, they get closer and closer to each other, and they approach this point, but they never reach it. So that's why I didn't make a filled circle, because they never reach this point. In this case, this point, even though it does not belong to A, and even though the set consists of just random points, this is considered a cluster point, and it's easy to see why. Since the points, they converge to this one point, if I draw any circle centered on this point, there will be points inside it. No matter how small I draw the circle, there will always be points inside it. So it is a cluster point. So for example, so in this case, there is a cluster point, and it's not in the set. Okay, and there is just one cluster point. So it doesn't need to be like a nice field shape to have a cluster point. It can be a bunch of numbers. All we need is that these points, they actually converge to something. If they are just scattered around, if they're just scattered around, then I mean there's no cluster point. But if they approach something, and there are like infinitely many points getting closer and closer to something, then that thing they're getting close to is an accumulation point. Okay? One last thing before we move on. If P is a cluster point, as I said, by definition, if I draw any circle centered at P, there will be at least one point of a set A inside it. Okay? Great. But if you remember what the definition of being inside a circle is that this distance d between these 2 points is less than or equal to the radius of the circle. So what we really mean when we talk about cluster points is that for any distance d from that point, there is a point in the set A that is a distance of at most d. So if I want, for example, I want a point that is, I don't know, a distance of, like, if I take like a given distance, I will always find a point whose distance to P is smaller than the distance I defined. So that is another way to define a cluster point. So basically, I have elements of the set as close to the point as I want. Okay? Nice. Now moving on to the actual exercise. So there it is. A set A is said to be bounded if all of its points are within a given distance to the origin. So for example, if I let's draw like the coordinates, like the x-axis and the y-axis. And any set A is said to be bounded if they are some distance from the origin. So I can draw a circle centered at the origin that contains A. So for example, this will be such a circle. All of the elements of A are within this circle, which means they are within some distance to the origin. So basically, a set is bounded if they don't have points as far to the origin as you want. So there is like a maximum distance, and all of the points of A are within that maximum distance. So what we need to show is that if A is a bounded set, which means it's within some circle, and it has infinitely many points, then it has at least one cluster point. That's what I mean when I say that if I have infinitely many points inside a circle, then they must cluster somewhere. So what I mean with that is for any set that has infinitely many points and that's inside this circle, there is one point, at least one point, that if I take any distance from that point, I will definitely find a point of A within that distance. That's what I want to show. Again, you can try to see this for yourself. It's quite easy. If you have like a circle, oh, that's not a circle. Okay, better. If I try to spread like infinitely many points here, they will cluster up somewhere. I can place infinitely many points and not have them clustered somewhere. So how do we prove this? How do we even prove this? Like, it seems quite obvious and it seems like intuitive, and you're like, yeah, sure, it's probably true. But how do you even tackle such a problem? How do you even start proving that there must be a cluster? So there's no cluster here because I haven't put infinitely many points here yet. But if I keep going, like let's say they cluster around here again, how do I prove they got a cluster? How do I prove they got a cluster somewhere? How do I do this? Well, here's a hint if you want to try to prove this by yourself. If you don't want the hint, just pause it now. But my hint is, try to find where this point is. Given the set, suppose you already have the set, try to find where this cluster may be, this cluster point, to be more precise. Where it is. Try to develop a way to find this. Like, given a set, try to develop some algorithm or something that gives you the exact position of that cluster point. Because if you do that, then you've basically proven that there is one. Because, well, you can always find one if they ask you to. So that's my hint. So if you want to try this for yourself, just pause the video and I'll be waiting for you. Okay, now let's prove this theorem. In order to do that, I actually developed two ways to prove this. I found two demonstrations. I found the first one that I decided to call the cross-scan solution. You see why I named it like that. And it's a bit more complicated, but it's actually rather nice to see. I found it very, very, very interesting. Like, the reasoning behind it, it's very interesting. So I want to show this. And after that, there will be another proof that I found online that I just gonna nickname it the Pinpoint proof, which is far easier, but it's not as nice to see as the first proof. So I'm gonna show both of them. And in the end, I'm gonna show how this theorem actually proves a remarkably important theorem called the Bolzano-Weierstrass Theorem. So let's jump to the first proof. The first way we're going to prove this theorem, which I decided to call the cross-scan proof, it basically relies on one idea. So imagine this is our set, for example, these bunch of points. Let me actually paint the circle to be of a lighter color, so you don't think that it's part of the set or anything. So imagine we have like these infinitely many points clustered together. What we're gonna do is basically scan them. So we're gonna draw a line, right? And we're gonna sweep through. We're gonna sweep through the. We're gonna sweep through the set, and we're gonna look for something. So for any point the line is in. So take this point, for example. What we're gonna do is we're gonna analyze everything that is to the left of the line, okay? And the question I'm gonna ask is, how many points are there on the left of this line. In this case, for example, see there are infinitely many points clustered here, so there are infinitely many points here. But if I keep sweeping through, so for example, now there are infinitely many, some of them are on the other side, but there are still infinitely many, and I keep going, until then, suddenly, oh, now there are finitely many numbers. There is a finitely many elements here. There are like some elements around here. There are a bunch of elements overall, but there are the number of elements here is finite. That's what we're gonna look for. We're gonna analyze when the number of elements to the left of this line is finite. Okay? So now I'm gonna switch to GeoGebra so we can have like a better view of what we're doing. Okay, great. Imagine this set in blue is our desired set, the set we want to show there is an accumulation point. I mean, obviously there is, but the idea is that this must work for any set. I'm gonna show here for one specific set, so you can understand how the proof goes. But so for example, take this set. See this line? We're gonna use this line to see how many elements of this set is to the left of this line. So right now I'm investigating basically this whole circle. The idea of this circle is that since our set is bounded, there is a circle to which our set is completely inside it. So that's why I drew this circle. In this case, the circle has radius 1, but it can be whatever radius. The only thing we need is to have at least one circle to which the set is entirely contained. So great. So what we're gonna do, all this red is basically because since the line is completely to the right of the circle, we're analyzing basically every point inside the sphere. But if we approach the set, again, the red part is all we're investigating. So you see this part, there is still part of the set in it, and there are infinitely many points in here. So there are still infinitely many points to the left of this line. So we keep going, there are still infinitely many points. Right now there are points here, there are infinitely many of them. So you keep going, and then all of a sudden it turns blue. If it turns blue, it means that there are now finitely many numbers to the right of this line. In this case, there are exactly 0, but there could be like some scattered points around here. Doesn't really matter. The only thing that's important is that now there are finitely many numbers here. So if you take a look, there is like a place where we stop having infinitely many points and we start getting finitely many of them. So we want to take a closer look into where this happens. So we see that it's basically around here. And what is the idea? If we draw this line where the set changes from red to blue, if we draw this line, any line we draw to the right of it will have infinitely many points. So you can see if I draw a line here, if you take a look at this green line, if you pay close attention to it, you see that part of the set is to the left of it, which means there are infinitely many points here, right? So you can see there are infinitely many points to the left of it, and it doesn't matter how small this value of epsilon is. Any line to the right of it will have infinitely many points to the left of it, if that makes sense. So in this orange region, there will be infinitely many points, precisely in this small region right here. Okay? And it doesn't matter, like I can get as close to this red line I want, there will still be infinitely elements in this tiny bit here. Okay? On the other hand, if I draw a line to the left of it, any point to the left of this line will have a finite number of elements. In this case, there are 0, but it could be like 3, 7, 400, or whatever. There could be some scatter points. It doesn't matter. There are finitely many. And I mean, I can keep going, there will be finitely many, and I can get as close to this red line I want. and there will still be finitely many elements. So the idea is that on this line, if I draw any line to the right of it, there will be infinitely many points. And if I draw any line to the left of it, there will be finitely many points. To the left of the line, always to the left of the line, okay? So great, if there are infinitely many elements in this line, I mean, if there are infinitely elements to the left of this line, if there are finitely elements to the left of this other line, then do you agree that the amount of elements in this region will be infinite minus a finite number, and therefore there will be infinitely many elements in this stripe? Do you agree with that? So great. Now we know there are infinitely many elements in this stripe. So what do we do next? Well, what we're gonna do is now we're gonna scan it vertically. So you see the infinitely many elements, they are right here, okay? And one quick detail, I can like make this stripe as narrow as I want, and there will still be infinitely many elements here, okay? I'm gonna make it a bit bigger so you can see better. So great. So now we're gonna scan it vertically. So we're gonna take some line and we're gonna analyze how many elements of the set are within this stripe and below this line. So now there are currently infinitely many, precisely here, and we're gonna move down. And now there are still infinitely many elements right here. And as you go down, and then it suddenly becomes finite. So you use the same line of reasoning that right now there are right now there are finitely many, and here there are infinitely many. So there must be like some point in here to which every line above will have infinitely many points, and every line below will have finitely many points. So by taking this very division where every line above it will have infinitely many points below. So you can see it here. So this blue line, any line drawn above it, will have infinitely many points below it. So in this case, those points are all here. And I can make this as big as I want, or as small as I want. And there will still be infinitely many points in this tiny bit. And any line that I draw below it will have finitely many points. Okay, great. So there must be an infinite amount of points in between those lines. Okay, if there are infinitely many points below this line, and finitely many points below this line, then there must be infinitely many points in this very region. And that is the great thing, because I can just reduce the value like this. I can just squeeze this stripe, and I can also squeeze it in the other way. So I can just reduce it right here. And if I go back, I'll have a tiny region that I know for sure there are infinitely many points here. And I'm gonna show how having infinitely many points in a square or a rectangle as small as you want basically proves that there is a cluster point in there. But it's kind of obvious, because there will be infinitely many points clustered in this very rectangle. Okay. However, there is a problem. There is a big problem. So to show this problem, let me just increase it back again. To show this problem, I'm gonna switch to another example. Okay. Now let's take a look at this other example. Now we have another set, right? This region here, which is like defined by this line, this parabola, and this circumference. Let's do the same process for this set to try and find a cluster point, right? Or like a rectangle with infinitely many points inside it. So what we're gonna do is we're gonna scan it from right to left. So we're gonna just keep going. There are still infinitely many points. There are like infinitely many points around here. There are still infinitely many points to the left of this line. So there's like this tiny rectangle which has like this kind of rectangle with infinitely many points, and I can keep going. Oh, now it's finite. Now there are finitely many points. So the region in between must be like around here. Okay? So next step, you see that, you know, any line drawn to the right of it will have infinitely many points to the left of it. You can see that if I take like this, there will be infinitely many points in this region, so there will be infinitely many points to the left of this line. If I take another line to the left of it, there will be finitely many points to the left. In this case, again, it's just 0, but there could be more. And therefore, there will be infinitely many points in this very stripe. Okay? Great. And I mean, I can make this stripe as small as I want. Now, what I'm gonna do is, actually I'm gonna increase this a bit because so it's easier to see. Now I'm gonna scan this vertically. So now there are still infinitely many points below it, and as I go down, there are still infinitely many points below it, infinitely many points below it, infinitely many points. Well, oh, and now there are finitely many points below this line within this stripe. Okay, great. So let's find the point, like the very division, which is around here. Okay, so let's say we found this vertical line that, you know, is the boundary that for every point above there will be infinitely many points below it, right? You can clearly see that. And for any point below it, there will be finitely many points below. Okay, same thing we did with the x-axis. So if there are infinitely many points here and finitely many points here, there will be infinitely many points in, you know, this region, which is the difference of them both. So great. We've done it, right? We're great. We've did it. Now we can find. We found a rectangle with infinitely many points inside it, and I can squeeze it. Right? I can squeeze it vertically and horizontally, and have a rectangle as tight as I can. Right? Well, no. Actually, no. Let's go back here. You see the way I did this right here, right now. There are I am just slightly above that limit line, so there are infinitely many points below. But if I squeeze this, if I squeeze the stripe this way, what will happen is now there will be finitely many points, and you see that now that division won't be here. It will actually be a bit above, it will be here, it will be right here. And if I squeeze it more, then it will still go up a little bit. So if I zoom in here, it will still go up, and if I squeeze it even more, you know, this line will keep going up until it gets to a limit. And then no matter how tight I squeeze it, it will never go higher than that. Okay? So this, like, when you squeeze it, this horizontal limit line will go up and go up and go up and go up until it gets to this very limit. And we're not gonna stop like halfway through and take like this limit to be our horizontal line. We'll take the very limit. We'll take the line in this very limit, okay? As you go up, you know, as you squeeze it, we're gonna take this point. Okay? So if you see now, any line above this new threshold will have infinitely many points below it, and any line below it will have finitely many points, right? So if I go back, let me make this real big so we can see. So any line above it will have infinitely many points. You can see them right here. And every line below will have finitely many points, right? No. See, in this case, for example, there's this tiny bit. The reason is because this threshold is just for the limit case. If you take like any finite like stripe, this won't be the limit case. So there may be a tiny bit here that makes this region down here have infinitely many points, and we want this to have finitely many points. But this is not a loss case, because what I can do is, and I can squeeze the horizontal line, the vertical line, until it gets to a point where there is no there's no, where those infinitely many points that were here, they just go away as if I squeeze it tight enough. So great. If I take like a smaller epsilon, there will be still infinitely many points, but I can squeeze this until I get finitely many points. And I can even keep going in order to have this size to be like this size to be not bigger than this size. So if I have like a distance of like 0.3 here, I can continue squeezing it until I have a 0.3 or less. Okay. And then now, like for any epsilon prime, I can like just squeeze it in order to have finitely many points. And then, you know, if there are infinitely many points here and finitely many points, well, there will be infinitely many points in this rectangle. And I just can do this whenever I want. I can just keep squeezing it. And you can see that, you know, I can have infinitely many points in a rectangle as small as I want. Great. The last thing to do is to prove this is a cluster point. This is actually pretty simple. So let's say I have a given circle, right, of some radius. I want to prove that there is at least one point of this set inside this circle. What we can do is simply draw this rectangle, and you see that if I draw this circle to be a bit bigger than this rectangle, or rather, if I draw this rectangle to be a bit smaller than the circle, right? Because given a circle, we want to find the rectangle. If I make a rectangle that is just slightly smaller, well, I know there are infinitely many points here, so there must be at least one point in here, and if there's one point in here, there's one point inside this circle, and I can do this with whatever circle. Like if I have this, oh no, the distance here is too big, but I can just, you know, I can just squeeze it and there will be no problem. And now, you know, this rectangle is completely inside the circle, and there are infinitely many points in this rectangle, so there's at least one point in this circle. So we've basically proven that if we just close this and we get to this point, this very point will be a cluster point. So we've basically proven this. This is the cross scan proof. I called it cross scan because there's, you know, a vertical line sweeping through it, and then a horizontal line sweeping through it. So it's kind of like a double scan. Great. Now this proof was a bit complicated, but there's actually a proof that's much simpler that I decided to call the pinpoint proof. And let's take a look at it right now. Now this second proof it's much easier than the first one. It's not as nice to see, but it's also a really neat proof. So what we're gonna do is we're gonna take this circle. First of all, if all the points are inside the circle, then all the points must be inside this rectangle too. So let me just draw this rectangle, or rather this square, since it's a circle. So if there are infinitely many points in this circle, there are infinitely many points in this square, right? So great. What I'm gonna do now is I'm gonna split this square into 4 parts. So I'm gonna make like a horizontal cut, and a vertical cut and a horizontal cut, and I'm gonna divide this into 4 parts. So we have the first part, the second one, the third one, and the fourth one. So great. What we do next is we're gonna take this first region, okay? Let's just give a priority to them. So this will be like number 1, this will be number 2, this will be number 3, and this will be number 4, okay? So I'm gonna take a look at the first region with their boundaries, and I'm gonna ask the following: are there infinitely many points in this region? If not, first of all, let's assume there isn't. In this example, there is, but let's assume there isn't. Then we're gonna move to the next one. So if there isn't, now we're gonna analyze this one, and then this one, and then this one. And there must be infinitely many points in at least one of them. Because, you know, there are, like, if you take all four of them and add together, there must be infinitely many points. So, okay, there are infinitely many points in this first one. So let's take a look at it. Okay, let's take a closer look. What we're gonna do next, we're gonna split them again. Okay, so we split them again, and we're gonna ask this again. This first region, are there infinitely many points here? Well, no, there is just one point, so we just completely disregard that. Now we take a look at this second region. Are there infinitely many points? Well, there are some points here, but they're more down below here, so let's assume there's not infinitely many points, just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 12-ish points. So no. Are there infinitely many points in this third region? Well, yes. So we're gonna split this into 4 regions again. Are there infinitely many points here? Yes. Let's split them again. Are there infinitely many points here? Yes. Split them again. Are there infinitely many points here? No. Are there infinitely many points here? Yes. So let's split them again, and you can keep going, and you see that you will kind of approach like a given region. Like you basically have a square as small as you want, with infinitely many points in it. So as you go on and go on and go on and go on, you'll find a square as small as you want with infinitely many points in it, and you can use the same argument as before to say that there must be a cluster point in it, and as you get smaller and smaller, it's going to approach a point. This point will be the cluster point. So by doing that, we've basically proven that there is a cluster point, and we could actually, you know, pinpoint it. That's why I decided to call it the pinpoint proof. It's not as nice as the first one. I mean, I think the first one is more visual and I like it more, but it's way easier to see and to understand and to see that this must be true. Like, I can do this iteratively, and I'll get like smaller squares that have infinitely many points, and I can just keep going, and in the limit process I'll have one point, which is the cluster point. So great, we've proven it. Lastly, we can use that theorem, like that exercise we've just proved, to prove a great theorem called the Bolzano-Weierstrass Theorem. This theorem states that any bounded sequence has a convergent subsequence. So what does it mean? Like, bounded sequence, convergent subsequence, what is this? Well, a sequence is basically just a bunch of points that does not form like this is not a sequence because it is like a closed space. But like if I have like a bunch of points, one second. If I have like a bunch of points and there are infinitely many of them, a sequence has to have infinitely many of them. Then that is a sequence, because you can take like the first point I drew will be point number 1, the second one will be point number 2, and so on, and there must be infinitely many of them. So if I just keep going and I make infinitely many points, I'll have a sequence. So the sequence it's basically a bunch of points that I can put in a list. So the first point is this one, the second one is this point, and so on, and I have infinitely many points. Okay? A subsequence is simply a sequence made from some of the elements of the first sequence. So I have the first list, I just take some of the elements, and I have another list which is still infinite. That is a subsequence. And a convergent subsequence is basically what we saw before. It's basically a sequence that as you go on and on and on and on and on, it approaches something. It approaches some point. This is a convergent sequence, right? And lastly, a bounded sequence. What is a bounded sequence? Well, for example, if I have like this sequence of points and it just keeps going, and let's just say there are infinitely many of them here. A bounded sequence is basically the same idea of a bounded set. There is a circle around it that I can draw, and all the points will be within that circle. So basically the points, they just don't shoot off to infinity. So the Bolzano-Weierstrass theorem says that any bounded sequence has a convergent subsequence. So how do we prove this? Suppose we're working with, I mean, this sequence is not nicely drawn. Let me make another one. So suppose we have like some sequence with infinitely many elements. I can show you that there must be a subsequence which converges to a point. And I'm going to show that by creating this subsequence. So first of all, this sequence is bounded, right? So there must be a circle that contains it. Great. Now, if I take this sequence, I can treat it as a set, right? Since it's a bunch of points, and a set is just a collection of things. So it is a set too. So okay, now I have a set that is bounded and has infinitely many elements. So I can use what I just proved there to say there must be an accumulation point somewhere. Let's say this accumulation point is here. Okay? Now I'm gonna show how to create a sequence from this cluster point. Okay? What we're gonna do is we're gonna draw a circle with whatever radius we want. So just draw a circle here. And since it's an accumulation point, there must be a point within this circle. So let's take this point, for example. Right? There's at least one. Let's take this one. What we're going to do next is we're going to take the distance here. Let me draw this in blue. We're going to take this distance, okay, d. I'm going to divide this distance by 2, okay? I'm going to divide this distance by 2, and I'm going to draw a new circle with half this distance. So that first point will not be in this new circle, right? But now, since it's an accumulation point, there must be a second point somewhere here that is within this distance. Let's take this one, for example. And let's draw the circle around it, right? With half the distance. And we're going to get a new point. And I can just draw another circle, get a new point, and just keep going, keep going, keep going. And I'll have a list of points. So this is the first point. This is the second one, the third one, and so on, so on, so on, so on, so forth. And I'll basically have a sequence. And this, I'll have a subsequence, since all the elements of this sequence are elements of the original sequence. So I'll have a subsequence, and this sequence converges because the distance of those points, so the distance from those points to that cluster point will just go down, since I'm just reducing the radius. So the points will always be approaching this cluster point as much as I desire. So not only we know that this subsequence converges, we know it converges to that cluster point. So basically we've proven the Bolzano-Weierstrass theorem. So any sequence that you have, if it's bounded, it will have a convergent subsequence. And just reminding you, a sequence must have infinitely many points. This theorem is really important because it is used to prove a bunch of other theorems that are also like extremely important. So I just found this overall really cool to work with. Like this problem, like the problem I've showed before, it appeared in my Calculus 2 book, and I mean I still don't know why the author put that exercise in there, since it's kind of, I mean, he was talking about cluster points, so fair enough, but it was a bit, more complex than I was expecting, but it was still really fun, and the proofs I found were very, very beautiful. Like, they're really neat, if you know what I mean. They are oddly neat, So I decided to share this with you. One last thing before I end this video is that everything I showed you here works for any number of dimensions. So it doesn't work only for 2 dimensions. So for example, if you're working with 1 dimension, then a circle would be just an interval. And the statement would be that if I had an interval, and the interval wasn't like, it had a finite size, it wasn't like infinite or anything, and I try to put infinitely many points inside it, then they would cluster somewhere in this interval. Also, it works on 3 dimensions, so if I have a sphere and I try to put infinitely many points inside it, they will cluster somewhere. And this works for more dimensions, so it works for 4 dimensions, 5 dimensions, or any number of dimensions you want. And the Bolzano-Weierstrass theorem also works for any number of dimensions. I'll leave the details for the proofs up to you. The pinpoint proof should be easy to generalize for more dimensions. The double scan one should be a bit more complicated, but it should also be doable. And that's it. Thank you so much for watching, and I hope to see you here any day soon. Later.